right, welcome back to a new chapter. We are starting chapter 8, which is vectors. Vectors should be really familiar if you're in physics. You should have talked about vectors a lot. A vector is a quantity that has both magnitude and direction. A vector is represented geometrically by a directed line segment. A directed line segment with an initial point P and a terminal point Q is shown right here. The length of the line segment represents the magnitude of the vector. The direction of the arrowhead indicates the direction of the vector. We could call this vector A and write it like this, or because it goes from P to Q, we could call it vector PQ and write it like this. The magnitude of a vector we write by putting the vector inside these little like absolute value bars. They're not really absolute value bars, but they look like absolute value bars. If a vector has its initial point at the origin, it is in standard position. The direction of the vector is the directed angle between the positive x-axis and the vector. So the direction of this vector is 45 degrees because this angle is 45 degrees. If both the initial point and the terminal point are at the origin, the vector is the zero vector. And you write that like this. The magnitude of the zero vector is 0, and it can be in any direction because it's got a magnitude of 0. It's just a dot. Here are some vectors. Vector y and vector z are equal because they have the same direction and the same magnitude. Here, vector v and vector u are equal. X and w have the same direction, but they don't have the same magnitude, so they are not equal. The magnitude of v and y are the same, but they have different directions, so they are not equal. In order for vectors to be equal, they have to have the same direction and the same magnitude. The sum of two or more vectors is called the resultant of the vectors. There are two methods that you can use to find the resultant. One is called the parallelogram method. So you draw the vectors so that their initial points are the same. Then you draw lines to form a parallelogram, and the diagonal from the initial point to the opposite vertex is the resultant. The triangle method. You draw the vectors one after another, placing the initial point of each successive vector at the terminal point of the previous vector. So you start here and go to the tip here, and then you put the tail of this one and then the tip here, and you do that for as many vectors as you have, and then you connect them with the resultant. This is also called the tip to tail method, and personally that's my favorite. So find the sum of vector v and w using the parallelogram method, the triangle method, and then compare the results. So gonna have to approximate here, but if I draw vector v like this and vector w like this, all right, using the parallelogram method, I'm going to make a parallelogram, and the resultant is going to be this. V plus W. Using the triangle method, I would start with vector v, and then I would do vector w, and then v plus w would be here. And hey, look at that. The two vectors are equal. All right, so here's a better drawing. right? You put the two ends together, and you make the parallelogram, and the diagonal of the parallelogram is the sum of your vectors. Or you do the tip to tail and make the triangle. And you get two vectors that are the same. An advanced glider, known as a sailplane, has high maneuverability and glide capabilities. The Ventus 2B sailplane placed first at the World Soaring Contest in New Zealand. At one competition, a sailplane traveled forward at a rate of 8 meters per second, and it descended at a rate of 4 meters per second. Determine the magnitude of the resultant velocity of the sailplane. So, travels forward at 8 meters per second, and it descends at 4 meters per second. So using our triangle method, this is going to be the vector. We'll call it v. What is the magnitude of this vector? Well, this makes a right triangle, which means we can use Pythagorean theorem. So, 8 squared is 64, 4 squared is 16. So that is going to be 80 equals magnitude squared. So the magnitude of this vector is the square root of 80, which is going to be a little bit less than 9. 8.9. Don't forget your units. Two vectors are opposites if they have the same magnitude and opposite directions. So vector g and vector h are opposites. Vector I and vector j are opposites. The opposite of a vector is denoted by making it negative. You can use opposite vectors to subtract vectors. So g minus h is g plus negative h. A quantity with only magnitude is called a scalar quantity. Examples of scalars include mass, length, time, and temperature. Numbers can be used to measure scalar quantities are called scalars. The product of a scalar k and a vector a is a vector with the same direction as vector a and a magnitude of ka. If k is greater than 0. If your scalar is negative, the vector has the opposite direction of a and a magnitude of ka. So use the triangle method to find 2v minus 1/2 w. So if this is vector v, then 2v is going to be in the same direction, but twice as long. If this is w, negative 1/2 w is going to be half as long and in the opposite direction. Arrange them so that they are tip to tail, and you get the resultant vector. Looks like this. That would be your 2v minus 1/2 w. Two or more vectors are parallel if and only if they have the same or opposite directions. Vectors I and j have opposite directions and they're parallel. Vectors L and K are parallel and have the same direction. Two or more vectors whose sum is a given vector are called components of the given vector. Components can have any direction. Often it is useful to express a vector as the sum of two perpendicular components. In the figure right, P is the vertical component of vector x and Q is the horizontal component of vector x. But I could have any components. I could have components that look like this, or I could have components that look like this, or I could have components that look like this. Right? I can have any two or more vectors that add up to make vector x. But usually we're going to do horizontal and vertical components because those are actually like useful. A ship leaving port sails for 75 miles in a direction 35 degrees north of due east. Find the magnitude of the vertical and horizontal components. This is where it's important to remember your SOHCAHTOA. Remember that? So, if I want to find x, I'm using this angle of 35 degrees. X is going to be the adjacent side. 75 is the hypotenuse. Adjacent and hypotenuse is cosine. So I can write this as cosine of 35 equals the adjacent side x over the hypotenuse 75 and solve for x. And so I multiply both sides by 75 and x is going to be 75 cosine of 35 degrees. And I plug that into my calculator and come up with 61.4 miles in this case. Similarly, y is going to be my opposite side. So sine of 35 degrees is y over 75. So y equals 75 sine of 35. And when I put that into the calculator, that gives me 43.0 miles. A piling for a high-rise building is pushed by two bulldozers at exactly the same time. One bulldozer exerts a force of 1,550 pounds in a westerly direction. The other bulldozer pushes the piling with a force of 3,050 pounds in a northerly direction. What is the magnitude of the resultant force upon the piling to the nearest 10 pounds? So we have a force of 1,550 pounds in a westerly direction and 3,050 pounds in a northerly direction. The resultant vector is going to be the magnitude of the resultant vector is going to be the length of this hypotenuse. So we'll call this resultant vector r. Magnitude of r squared is 1,550 squared plus 3,050 squared, which is was that 2,492,500? And so then the magnitude of I don't know why it's not letting me erase that, but the magnitude of this is going to be the square root of 2,492,500, which is 1,579. Now it says to the nearest 10 pounds, so 1,580. We also want to find the direction of the resulting force. So we're going to find this angle theta. I realized I drew my diagram going east instead of going west. Yeah, should look like that. It doesn't change the math, it just means that my diagram's a little bit off. There. Alright, so we want this angle. So we know the opposite and the adjacent sides. We're going to use tangent. Tangent of angle theta is the opposite side over the adjacent side. And so we can then to find angle theta, we're going to use the inverse tangent, which is going to be, do the inverse tangent of 3050 over 1550, which is 63 degrees. And then we also need the direction here, because this is not in standard form. So if we're talking about north and west, this is 60 degrees north of west, right? If you're going west, you then turn 63 degrees to the north. So 63 degrees north of west. And that's it for 8.1. Tune in next time for 8.2, more vectors.